previous lecture, we have discussed about the basic integrated circuit. Now today we will see what are the limitations of this basic integrated circuit and why we have to go for a modified integrated circuit, which is also known as a practical integrator. So in a basically integrated circuit, already you know that in a feedback part, the capacitor is connected, at the input the resistance R1 is connected, and we know that the output voltage of the integrator is given by minus 1 upon R1 CF integration of your input voltage VI dt plus some integration constant will be there. So in this way, here the circuit is going to integrate your input signal. Then we have seen that at the input, if we apply a sine wave, then the output is going to be a cos wave. If we apply a square wave, then the output is going to be a triangle wave. If we apply a step input signal, then it will give you, integrator will give you the output like a ramp voltage. So in this way, this integrator is going to change the waveform of your input signal. Then we have discussed what is the gain of this amplifier. We have derived that the gain of this amplifier is given by 1 upon upon 2 pi R1 CF into F. That F is the input frequency. Correct? Now here if you see that when there will be a no AC signal, or you can say we apply a DC. So when the input is DC, for the DC the frequency is going to be 0, and in that case if you calculate the gain, then this is going to be infinite. So the output of your integrated circuit is going to be very large. And why this is going to happen? Because when this frequency is 0, DC input signal is there. In that case, if you calculate the reactance of the capacitor is going to be infinite. And as a result, the gain of the amplifier is also going to be infinite. So the output voltage is very large. Now here, if my input voltage is 0, remember, input voltage is 0, but when we consider that the practical OPAMP instead of a ideal OPAMP, if we consider the practical OPAMP, then we know that in a practical OPAMP, always there is a offset voltage is there. Input offset voltage is present. Between the inverting and non-inverting terminal. Now, this input offset voltage can be a positive or it can be a negative. Now, this input offset voltage is also in order of few millivolt. Already we know that this offset voltage is in order of millivolt. Now, in this case, the gain of the amplifier is very large. So, what will happen if the input signal is very low? Then still, there you will get a very large output voltage. And here if this input voltage is positive, then what will happen? Your capacitor is go on charging or the discharging, and as a result, initially you will get the output voltage. Due to this offset voltage, remember, here you will get the output voltage like this. It is go on decreasing because for the DC you will get a ramp voltage. So this voltage is go on increasing in a negative side, and then it is going to be a saturated, because the maximum output voltage of the operational amplifier will be always a plus saturation or a minus saturation. So here you will get this voltage A minus V saturation. If my input offset voltage is a positive, if we have a negative input offset voltage, then in that case the output voltage is go on increasing, and then it is going to be a saturated at this voltage of V saturation. Correct? So due to the input offset voltage as well as due to the bias current, here always there will be a flow of a bias current will be there in case of a practical operational amplifier. So due to that capacitor is going to be charged or it is going to be a discharge. So now what will happen? That when we apply some voltage here at the input, if some voltage is present here, then the output voltage consists of your input voltage also, as well as it will consist of your a saturation voltage. So as a result, you will not get a true integration of your input signal. Your input signal is going to be a distorted. You will get the error in a integration. So again I will tell you that here due to the input offset voltage as well as due to the bias current, some voltage is going to be present in the output, and that is going to affect the result. Now when you apply any input signal, then this input signal is going to be integrated as well as, so you will get the output of the integrator of your input signal plus some error voltage will be also present. That is due to the offset voltage as well as due to the bias current. And as a result, your input signal is going to be a distorted. And you will not get a true integration of your input signal. So this is the basic limitation of the integrator. Then also we have seen the bandwidth of this integrator is very, very small. Correct? And that's why we have to modify this integrator circuit so that at a DC voltage the gain will not be a infinite. Gain will not be a infinite, and we can minimize the effect of a input bias current and the offset voltage. So now let us see what is the practical integrator circuit. Now here you can see that in a practical integrator circuit, across the capacitor, feedback capacitor, one more resistance is connected, and this resistance is going to be a very, very large. Here this practical integrator is also known as a lossy integrator. It is also known as a lossy integrator. Sometimes in a practical integrator, we are also connecting a one resistance in a non-inverting terminal that you already know. It is known as a R compensation. So to minimize the effect of a bias current, always we are connecting a one resistance at a non-inverting terminal, and it is known as a bias compensation. The value of this bias compensation you can calculate by this formula, that the R1 parallel to Rf. So now here in this case what will happen? Whatever the bias current will be there, this bias current will pass through the resistance Rf instead of a Cf. Now when your input voltage, here remember, when your input voltage is 0 or the frequency f is 0, means you are applying a DC voltage. In that case, this capacitor reactance Xc is going to be infinite. Means this is working as an open circuit. Capacitor will work as an open circuit. But still there will be a feedback part that is due to the resistance Rf. So you will not get a infinite voltage gain. So when this frequency or your input voltage is zero, capacitor is open, working as an open circuit, but we have connected a one resistance Rf parallel to C. So in that case, the circuit will work as simply a inverting amplifier, and the gain of the amplifier you can say it is minus Rf by R1. Here we can write, when this F is equal to 0, your input voltage is 0, then the reactance of the capacitor is going to be infinite, means the capacitor work as open circuit. But the RF is connected across the capacitor so that circuit behave like a inverting amplifier. And in this case, the gain of this amplifier will not be infinite, but here you can say the gain of the amplifier is equal to Rf by R1. So in basic integrator, what has happened when the F was 0, the gain was infinite. Now this gain is reduced to Rf by R1. Okay. Now let us see what is the gain of this a practical integrator circuit. So gain of this amplifier and we know that the gain is given by gain of this inverting amplifier is given by minus Rf by R1. Correct? But now here, instead of Rf, we have also a capacitor. So we have to consider this, and both are in parallel. So it is given as Rf parallel Xcf divided by resistance R1. Correct? So now let us see what is Rf parallel Xcf. And already you know that is Rf and Xcf means 1 upon j omega Cf divided by, we can write Rf plus 1 upon j omega Cf. Then this will be here 1 upon j omega Cf multiplied with Rf, you will get 1 plus j omega Rf Cf, and then it will be cancelled with this. So here you have Rf divided by 1 plus j omega Rf into Cf. Therefore, the gain of the amplifier, if I want to write, then the A is equal to minus. Now Rf is parallel Xcf means here Rf divided by 1 plus j omega Rf into Cf divided by AR1. And this thing I can write as minus Rf by R1 divided by 1 plus j omega Rf into Cf. So this is the gain of the amplifier, gain of the practical integrator circuit. Correct? Now here we will define one more term, that is a RFCA. Already you know it is a kind of a time constant, and the time constant is related with a frequency, correct? So this is representing a kind of a frequency also. Now here this thing I can write as A is equal to minus Rf by R1 divided by 1 plus J 2 pi F Rf into Cf. Correct? Now, here if you see that 2 pi RFCF here, this value 2 pi into RFCF is nothing but it is a reciprocal of some frequency, and therefore we can write this as A is equal to minus Rf by R1 divided by 1 plus J, then this frequency F is as it is divided by Fa. What is Fa? Fa we define as 1 upon 2 pi Rf into Cf. Remember. And finally, if you want to write what is the gain of this practical integrator circuit, then we can write as that magnitude of this gain of this integrated circuit is written as this is mod A equal to Rf by R1 divided by under root of, here we have 1 plus J F by Fa, and that will be written as 1 upon F by Fa whole square. Correct? Where the Fa is given as 1 upon 2 pi RFCF. Remember, this frequency is known as a break frequency, or it is known as a corner frequency of a integrator. Fa is known as the corner frequency of the integrator. Now we will see what will be the frequency response of your practical integrator circuit. Okay? Here, in this formula, we write that the when F is equal to 0, F is equal to 0 means we applied a DC voltage. So in that case, the gain of the amplifier is given as Rf by R1 divided by under root of 1 plus, and this is going to be a 0. So the gain of the amplifier is equal to Rf by R1, simply. And Rf by R1 is indicating what? That when your input voltage is DC, means the OPAMP behaves like a inverting amplifier, where the gain of the amplifier is given by Rf by R1. So initially in a basic integrator we have seen the gain of a integrator was infinite. Now it has reduced to Rf by R1. So whenever the frequency whenever my input frequency is always less than FA, remember, when it is less than FA, always the gain of the amplifier will be RF by R1. If we calculate this gain in dB, then this is written as a 20 log RF by R1. In dB, it is 20 log RF by R1. So, if we see the frequency response, here we have frequency, we have this gain that is in dB, okay? And if you remember that for a basic integrator, the graph was like this. Correct? At f is equal to 0. Here we have f is equal to 0. The gain was a very high, like a 100 dB. This is a basic integrator. Now you can see at f is equal to 0, the gain is given by 20 log RF by R1. So somewhere here you will get this point of 20 log RF by R1. So gain is reduced from 100 dB to 20 log RF by R1. Now for all the frequency, remember, for all the frequency which is less than FA, here in this formula that you can calculate, if my input frequency is less than FA, then always the gain of this amplifier will be a 20 log RF by R1 will be there. So here if I will increase, that is a 100 Hz, 200 Hz, 300 Hz, then the gain of this amplifier is almost going to remain constant. Like this. But now, when the frequency is greater than FA, here, when f is greater than FA, now here you can calculate f is greater than FA, then as the frequency increase, the gain of the amplifier is go on decreasing. The f is greater than FA, the gain is decreasing. So here in this case it will be decreased like this. Remember, it is going to decrease in this manner. So now if this is my input frequency, f is equal to FA, then what will happen? See, when the input frequency is f is equal to fa, then the gain of this integrator is given by Rf by R1 divided by under root of 1 plus 1 will be there. Here f is equal to fa, so this is a and under root of 1 plus 1. So under root 2 and 1 upon under root 2 is nothing but 0.707 Rf by R1. Okay? And if we calculate in dB, then the 20 log mod A is equal to here you can write that 20 log 0.707 plus a 20 log Rf by R1. We are taking the log on both the sides because we want to calculate the gain in dB. And this 20 log 0.707 is nothing but it is a minus 3 dB. Remember, so you can calculate with the calculator. So in this case, the 20 log or the gain of this amplifier is 20 log Rf by R1 minus 3 dB. Correct? So if I want to find out the frequency Fa, then how we can find out? This is a 20 log Rf by R1 and somewhere here this is minus 3 dB will be there. You draw a line like this and here you will get the frequency Fa, and already you know that this frequency is nothing but it is a Fb. Already we have defined in a basic integrator that where the gain of the amplifier is unity or a 0 dB, that frequency is known as Fb, and here when the gain of the integrator reduced by 3 dB, that is known as frequency Fa. So what does this mean? This indicates that the integration is taking place between Fa and Fb. This is a integration range, you can say. And for less than Fa, if the frequency is less than Fa, simply your integrator will work as a inverting amplifier. Simply it is a inverting amplifier. So here you can use this circuit for the integration if your input frequency is between Fa and Fb, you will get a true result of the true integration. Actually, at frequency Fa, you will get 50% of the integration. But at frequency Fb, you will have a 100% integration. At this frequency, the 50% result will be there, and at this frequency, the 100% result will be there. So what is the advantage here? Advantage is that when my input frequency is 0, so the gain of the amplifier is not infinite, but it reduced to 20 log Rf by R1. And here you can see the bandwidth is also increased. In a previous case, the bandwidth was very small. Now the bandwidth of the integrator is very large. Now what is the relation between Fa and Fb? Here we will see that relation. Remember we have defined FA is equal to, that is 1 upon 2 pi RF CF. Then we have defined the frequency FB, that is 1 upon 2 pi R1 CF. So if I will take this ratio, FB by FA, that is 1 upon 2 pi R1 CF into, this will be 2 pi RF CF will be there, and this will comes out to be a RF by R1. So FB by FA, this ratio is equal to RF by R1, and that is the gain of your amplifier circuit. Normally this gain of the amplifier, we are taking a 10. You can also have 15, 20, but practical integrated circuit, the normal value is a 10. And from that we can say that what is the relation between this? So here, FB by FA, FB by FA, and that is equal to a 10, and this indicate the FA must be equal to FB divided by 10. So FB frequency must be 10 times higher than the corner frequency FA. And this formula will be useful when you are designing the integrator circuit. Okay. Now why this is known as a lossy integrator. Here, whatever the current, when your DC input voltage is 0, or the input frequency is 0, at that time, there is a flow of a current through the resistance RF. And due to that, there will be a power dissipation. And this power dissipation is nothing but it is a kind of a loss of the energy. So when my input signal or the input frequency is 0, then the current is not flowing through the capacitor because it is behaved like an open circuit. The current will pass through the resistance RF and there will be a power dissipation in the RF. So that is a loss of the energy, and due to that this is known as a lossy integrator. So remember that this integrator circuit is useful at high frequency range. This integrator is useful at high frequency range. Here, what is the high frequency range? Means this. Between the frequency FA and FB. This is my a Q integration range. Okay. Now let us see one example how to design the integrator circuit. Design a practical integrator circuit with DC gain of 10 to integrate a square wave of a 10 kHz frequency. RF is 100 kilo. Now if you look at the circuit, that Now remember, this is a practical integrated circuit. Now we have to find out what should be the value of R1, RF and CF so that you can integrate the square wave of a 10 kilohertz. Here the gain of the integrator is given. That is a gain of the integrator is given, and already we know it is given by RF by R1, and this is equal to 10. But RF is given as 100 kilo. So R1 will be equal to RF divided by 100 kilo ohm. Sorry. So R1 is equal to RF by A. RF is a 100 kilo ohm and divided by gain is 10. So you will get R1 as a 10 kilo ohm. R1 as a 10 kilo. Means we have calculated the RF. RF is 100 kilo ohm. Then R1 is a 10 kilo ohm. Okay. Now we have to calculate the CF. And for the calculation of CF, we have the two formula of FA and FB. Here in our case, the FB, that is a frequency which you want to integrate, and it is given a 10 kilohertz. Correct? Now what is the relation between FA and FB? That FA is given as FB by 10. So here we have a 10 kilohertz divided by 10, and this corner frequency will come out to be a 1 kilohertz. This is a corner frequency. Now what is the formula for FA? FA is given by 1 upon 2 pi RF into CF. So the CF is 1 upon 2 pi RF into FA. And we put all this value, this will come out to be 1 upon 2 pi. RF is 100 kilo ohm, 100 into 10 is to 3. And my frequency FA is 1 kilohertz, so 10 is to 3. And if we calculate this, then this capacitor value comes out to be approximately a 16 nanofarad. So here we have to connect the capacitor of a 16 nanofarad. Correct? Now, what is R compensation? I already mentioned that R compensation is reducing the effect of a bias current. Correct? So, R compensation is given by R1 parallel RF. So, this is R1 into RF divided by R1 plus RF. And here we have a 1 kilo plus 100 kilo divided by 1 kilo, sorry, this is multiplied by 1 kilo plus 100 kilo. And this will come out to be a 9.09 kilo. So here we connect a resistance of 9 kilo ohm. So in this way you can design the practical integrator circuit. So what are the first step? First step means you take the formula for the gain. Then you decide what is my FB. From there you calculate what is a corner frequency FA, and from there you can find out a capacitance value CA. And finally, you have to calculate the value of the compensation resistance. So in this way, you can design the integrator circuit. Now in the next lecture, we will discuss about the differentiator. How this operational amplifier can be used for the differentiating the input signal.